continuation of the geometric algebra using this paper and space-time algebra as our foundation. And we have reached all the way to section 3.4. So we have done all of this material. And so now we will begin with section 3.4. So let's begin. So section 3.4 begins here, right? Begins here, and we had just finished this idea of reversion, and we left off with the definition of the inverse of any multivector. Of particular interest of inverse of multivectors is the inverse of the regular vectors. When I say regular vectors, I'm always referring to the four basis vectors from the Minkowski subspace of our Clifford algebra. So I wrote that down over here. This definition applied to a single vector, a basis vector, gamma mu. If it's defined this way, well, the reversion of a single vector is just the vector itself, and the reversion square is just gamma mu spacetime product with gamma mu. And we know what this spacetime product is. It's going to be gamma mu dot gamma mu, because the wedge part will be gone, right? Remember, every spacetime product of two vectors has the contraction and the inflation part, and I'm not even going to write it down because this needs to be kind of in your head at this point. So the inflation part goes away, leaving only the contraction part, and that contraction part is defined as eta mu mu, right? Gamma mu. So this can be broken down into gamma 0 inverse equals eta 0 0 gamma 0, which equals minus, which equals gamma 0. And then eta I, where I equals 1, 2, and 3, inverse is, not eta I, gamma I, is eta sub I, gamma I, which is minus gamma I. So we see that our basis vectors are their own inverse, or just their own inverse is minus times a factor of -1. And we'll use this in our next section, which we will begin now. So section 3.4, reciprocal bases, components, and tensors. So, when you read this, he's literally telling you the things you better understand when you're done with this section. And that's the way you read a paper, is you're assuming that the author is giving you a real clear roadmap into what they're doing. And we are going to check those topics off as we learn them. So to connect with the standard tensor analysis treatments of the electromagnetic field, where the electromagnetic field, is considered to be an antisymmetric rank 2 tensor F mu nu, we now briefly consider the various ways of expanding proper multivector quantities into components. Okay, so now I'm under the presumption that everybody here is following along, at least in the sense that we're trying to compress electromagnetism into a single equation, right? That's sort of what triggered this rabbit hole of geometric algebra that we're all enjoying together. So let's make sure we kind of, now I'm not going to review the tensor formalism of electromagnetism. Presumably you've done that, but let's look at just a few facts and just to sort of set the stage for what this all promises to deliver. So this is how the authors are talking about a rank 2 tensor that can be used to describe the electromagnetic field. Now, these are numbers, right? And we know that it is antisymmetric. So we know, and the authors have already said as much, that this equals minus F nu mu. Now, to understand, right now, these real numbers are not part of a literal vector space because we're treating this as a collection of numbers. Now, it is completely legitimate and probably better, and it's certainly the way I teach this material, is to understand this as a set of components that belong to basis vectors that are in a tensor product space where these basis vectors are functions that eat forms, dx alpha, dx beta. And these forms go into slots, and the slots get consumed by these functions that eat forms, and they do so with this factor out in front. And when you do this, this becomes the basis vector of your tensor, of the vector space of these tensors. Now, what usually happens, however, as I've said many, many times in these lessons, is that we kind of forego all of this stuff here, and we just work with the components. And the components themselves are real numbers, and the antisymmetry is captured in the antisymmetry of these components. Now, we can also understand this as the components of the forms themselves of partial mu wedge partial nu. Don't confuse these. These are not, this is a partial derivative operator, which is acting as a basis vector. It's not to be confused with gamma mu, right? These are not, this is not an equality, right? This is, if the confusion exists, it's because I write like a child. A criticism which has been levied against me with complete fairness for the past few years I've been doing this. But so they are now going to talk about tensors in this paper, I'm quite sure, of just in terms of the components themselves. They're not going to go to the tensor product space and introduce these basis vectors and these functions. But understand that we have to turn this now into geometric objects, which means somehow this has to be either a scalar, it has to be a vector, a grade 1 object, it has to be a grade 2 object, it has to be a grade 3 object, or it has to be a pseudoscalar, like that, right? And or some combination of them in principle, right? But that's the goal here, is we're going to take this tensor that we used and we're going to discover its analogy in the geometric algebra. Now, they also use the word proper here, right? Now, in this case, they're actually saying we're going to take expanding a proper object into components, right? So this time they are using the word proper to mean without reference to any particular reference frame, because certainly when you introduce components, components have to have a basis, and a basis is a selected reference frame. Okay, we shall see that we immediately recover and clarify the standard tensor analysis formulas, making the tensor analysis techniques available as a restricted consequence of the space-time algebra. And restricted consequence is, I guess, a fancy way of saying, buried inside space-time algebra is all the machinery you need to execute the full rank 2 tensor theory of the electromagnetic field. And then there's more on top of that. So going on, given a reference basis gamma sub mu, so now we've introduced a basis for M13, see? It is convenient to introduce a reciprocal basis of vectors. And now what we do is we define the reciprocal basis as it's another set of vectors in M13, right? And it's superscripted. And M13 superscript is simply gamma mu with a superscript mu is simply gamma mu inverse. Now, this could be confusing for those of you who study general relativity and previous tensor analysis, where we would know that that the basis vectors with lower subscripts, right? If your basis vector had a lower subscript, that might be an element of your underlying vector space, right? And we know that if the basis vector has a superscript, it should be an element of the dual space, right? Which is not. These are not the same spaces, right? That is how we've always learned about subscripts and superscripts. That is absolutely not what's happening here. They are both elements of the same space. So you can add, in principle, you could add without any trouble gamma 1 plus gamma 3 plus gamma 2. You could add that, and this is a legitimate vector. This sum is totally legit because everything in this chain lies inside the same vector space. So you can add them together. You can also take space-time products of them. You could take a space-time product of gamma 1 with gamma superscript 3, which would be the same as gamma 1, gamma 3 inverse, right? So that is a confusion that's potential there for new people who are new on the scene and or old on the scene. If you're new on the scene, I guess you just buy the definition. And there's the definition right here. And by the way, this actually is a definition. This is one that does legitimately deserve a 3-bar equal sign, because you are defining the superscript version to be the inverse, the space-time vector inverse of the subscript version. And of course, this only really applies to basis vectors, right? Because basis vectors are the ones that are given subscript. Now, what's kind of interesting is you can create a basis for M13 called the light cone basis, where the basis vectors are light-like. And there is a good reason to do that. There's plenty of formalisms for special relativity where being in the light cone basis is actually a good idea. And if you were in the light cone basis, then this wouldn't work, right? Because in the light cone basis, MM reversion is 0. But that's maybe a little bit... so I'm kind of curious to know how that would affect some of this analysis. It can't affect it too much, but it certainly affects this definition. But that aside, as long as you choose a reasonable basis, and the reasonable basis we generally will choose, just so it's clear, is gamma 0, the purely time-like basis vector, is often going to be chosen to be the 4 velocity of some material particle. And that's the same thing as taking a reference frame and moving into the frame of some particle, right? You're moving into the reference frame attached to some material object. And once you do that, gamma 0 points purely upward, and the world line of that particle will always be a straight line in that reference frame. So once you've done that, you definitely are not in light cone coordinates or in any danger of light cone coordinates. And you drive the space-like parts, to be very standard space-like parts. Of course, I'm losing a dimension in my little picture here. So I wouldn't worry too much about that little fact. I'm sure if it comes up and it's relevant, it'll be called out later. As far as the text goes, I feel like this probably should have landed right here at the tail end of that paragraph, and this should have been front and center. However, we've been warned that this is a textual error, right? And we should be able to see that. So this first part of the equality is just wrong, and it slipped past editing. So, but is that so obvious, right? Could we have detected that error ourselves? And it sure does look like something strange, because we know that gamma mu, gamma nu, has got to be gamma mu dot gamma nu, and now I have superscripts and subscripts, plus gamma mu wedge gamma nu, right? Well, I mean, this looks pretty close. If this part was 0, then this equality would be legit. The problem is this part's not always 0. First of all, we know that gamma subscript, we know that gamma superscript mu is co-aligned with gamma mu. It's in the same direction as gamma mu, and we know that because we solved it, right? The reversion does not change the vector itself for a regular vector, and the reversion squared is just a real number. So whatever direction gamma mu is in, it's going in the direction of its reversion, which is the same direction. So this guy here will be 0 when mu equals, when nu equals mu. But when nu does not equal mu, it will not be 0. But if you look at the way this is written, right, this is written, this part here, right, is written in total generality. So it's obviously incorrect because it only equals this dot product in the case where mu and nu are the same, which is exactly what's reflected by this part of the equality, the second part of the equality. Right, that is correct. So we've been warned. We were warned by a viewer that this was incorrect, and they're right. They're right. So this is the definition, of course, of the inverse. The space-time inverse breaks down to this delta function, and of course that's referring to the contraction part. All right. So moving on. This is an equality equally valid. This is an equally valid basis of vectors for M13 that satisfies the same metric relation. Gamma superscript mu dot gamma superscript nu equals eta superscript mu nu. And in flat space, the good news is eta with superscripts equals the same eta with subscripts. So clearly, each of the basis vectors that we work with, gamma 0, its reversion is equal to gamma 0, gamma 1, its reversion is superscript gamma 1, which equals minus gamma 1. You can clearly see that this is obviously in the same direction as this, right? Or is not linearly independent of this. I guess it's in the opposite direction, but it's certainly not linearly independent. It's co-aligned, which is sufficient to make sure that the wedge product between the two is definitely 0. And I'll just make this an I for 1, 2, and 3, right? So now the point being is that any basis vector that we've written before as say A, I, gamma I, can equally be written as AI gamma I. Nice. So any multivector M is a geometric object that can be expanded in any basis, including the reciprocal basis. Well, that's what we just said. For example, a vector V has these two expansions, which again is something what we just said, vector V. Now here, of course, the Einstein sum is not implied anymore. They've broken out the Einstein sum, but understand that we will use the Einstein sum all the time. And I think they do too, really. I think they're just blowing it up just for exposition here. But they show that you can blow these things up in both basis vectors. There is a question of what is the relationship between the superscript and the subscript. Now, the superscript stuff we normally call the contravariant components, and the subscript we call the covariant components, right? And usually, in the old way of doing it, gamma mu would be a basis, gamma superscript mu would be a basis vector for the dual space of the vector space. But that's not happening here. I can't emphasize that enough. This notation is confusing in that regard because there's a good chance that if you're studying geometric algebra, you know tensor algebra already, or tensor analysis, I should say, already. And this is going to be something that you're going to have to wrestle with, right? This is not the dual vector, right? Right? This isn't a duality relationship between this and this. This is a straight-up equality because everything lives in the same vector space here. For example, a vector V has these two expansions in terms of the reference basis and the reciprocal basis. Oh, so that's good. They're going to call this the reference basis. I'm going to try to use the language of the paper as often as I can. So the reference basis, right, and the reciprocal basis. Okay. Traditionally, the components, the components in the reference basis, which is given by gamma mu dot V, are called the contravariant components of V. Now, we're going to see this kind of thing a lot, and it shouldn't be too hard to follow, but if V is V mu gamma mu, then, well, let me change that to V nu gamma nu. then gamma mu dot v. Now, notice we're using this dot as though it's some operation that lives in our vector algebra. But remember, the dot is always just a convenient way of breaking down gamma mu v, the space-time product of two vectors. In this case, you'll get gamma mu dot v plus gamma mu wedge v. So understand that, yeah, we need to know how to do these calculations of the contracted part and the inflated part, but it's not a literal operation of the Clifford algebra. But anyway, this is going to clearly be gamma mu dot v nu gamma nu, but this is a real number, so it's v nu gamma mu dot gamma nu, and by definition, or by the way we've defined this, we use this equation right here, and we get delta mu nu. So we end up with v nu delta mu nu, which is v mu, which is what they're after here, right? That's sort of what they're saying. So we've kind of exercised that to understand how that all came about. So we understand that formula. I just want to make sure you don't start assuming that this is some sort of fundamental operation of the algebra. It definitely feels like it eventually, because we do use this operation a lot. Okay, traditionally the components, and this is how you extract, it's a way of extracting the components in the reference basis, are called contravariant components of V, while the components in the reciprocal basis, and you can repeat the same exercise we just did for this, are called the covariant components of V. Now, when I studied tensor analysis and taught tensor analysis, I made it very clear why the word contravariant was used and why the word covariant was used. I'm not going to go through that right now. Those of you who are here wondering why do they use contravariant, what is varying contra, what is varying co, forget about it. In this case where we're at, we don't want to talk about the things that are varying, and right, and in fact there really isn't anything in this particular we haven't done. It has to do with basis transformations and a few other things that we haven't reached yet. Just take these as the names, right? The contravariant components of V and the covariant components of V. What is important is that V is the geometric object itself, right? V is the actual thing that lives in space-time. And when you write down V mu, what you're actually writing down is this. You're just expressing V in a basis. You're going from the proper form to the relative form. And if the basis you use is the reference basis, then these components are just called contravariant components. If the basis you use is the reciprocal basis, if the basis you use is the reference basis, you get the contravariant components. If the basis you use is the reciprocal basis, you get the covariant components. And the relationship between the two is the same relationship as in our Minkowski geometric algebra. The relationship between the two is the same as with the basis vectors, meaning that the covariant version of, or I'm sorry, the contravariant version of V, is equal to the covariant version of V, but the contravariant version of that for V0, contravariant versions of the other ones differ by a minus sign. And let's see, what else we have here? We see here that they can be interpreted in different ways as different ways of expressing the same geometric object, right? And that's sort of the key here. The geometric object is what it is. You have to choose a basis to get its relative form. Evidently, from 3.20, we have V dot reference basis equals the contravariant part of V. Oh, I just did this, right? This will get you the contravariant component of V, and it equals eta mu mu times the covariant contribution V. I did it reverse, but it's still the same thing, which shows how the two component representations are related by the metric, which effectively raises or lowers the index. Right? So the mechanics is actually very much the same as from tensor analysis, but the interpretation of things is very different because, again, the reference and the reciprocal basis are in the same vector space. Now, it is true that any vector space, when you give it a basis, it does have a reciprocal basis. That's true for all vector spaces. It's just the notation we use in other branches of physics. This is this exact same notation, but that reciprocal basis is literally a different vector space altogether, and there's a lot of complications that are introduced, but not here. In here, it's all the same vector space. Then let's see. Since the graded basis elements of the spacetime algebra are constructed with the antisymmetric wedge product from the reference or reciprocal vector basis, then one can also expand a K-blade into redundant components that will be the same as the components of any rank K antisymmetric tensor. For example, a bivector F, notice the notation here, they're capital, bold, Roman letter, may be expanded into components as follows. So this is how they expand a bivector. And here's the bivector basis in the reference basis and the reciprocal basis. And the components are just given with superscripts or subscripts, the contravariant form or the covariant form. There's also presumably a mixed form out there. But notice how this is antisymmetric. F, mu, nu are antisymmetric, and you'll double count if you just were to sum this up. And the reason you double count is you'll get gamma 1 wedge gamma 2, and then you'll get gamma 2 gamma 1, and that'll have a negative sign relative to the gamma 1 gamma 2. But this will have a negative sign because that's antisymmetric, so you'll end up with literally twice as much. You'll end up with the gamma 1 to gamma 2 basis vector will have a component that's twice as big if you just summed it up this way because of the antisymmetry of the basis vectors. So that's where this 1/2 comes from. And there's no genius amount of thinking that requires you to understand, hey, this is just a different basis, and we have our convention that for this Einstein sum, we have this up-down convention, and we're explicitly showing the sum here, so the sum is a bit redundant. And it's another important thing to note that the bivector itself, that's a geometric object. This is the proper form. These are the relative forms, right? So let's attack this line here. The components, contravariant components, F mu nu is equal to gamma mu dot the proper form of F dotted into gamma nu. And notice that these are that this is the reciprocal forms of the basis vectors, right? So we have the contravariant components is the geometric object dotted into the reciprocal forms of the components. So let's exercise this as best we can, right? So I've written it down here. This is what we're after, right? The claim is that the contravariant components is this given by this formula, right? This formula here. So I immediately replace F, the proper form, with its relative form. So I get F alpha beta gamma alpha gamma beta. And notice this is in the reference frame. Now you'll see I forgot a 1/2 here, right? There should be a 1/2 here. And I forgot that 1/2. So then I pull out the real numbers and I'm left with just the basis vectors in all of these dot producted forms. Now this is our wedge product between alpha, and in case that's not clear, that's supposed to be an alpha, right? I'll make all my corrections in red here. So it's alpha wedge beta, which comes from the basis vectors of this. You still have the implied Einstein sum, and you take the dot products this way. Now, this is an example. We've memorized how to do this, right? We know that when we have A wedge B dot C, right, this dot product, this is the contraction part of the space-time product A wedge B C. This is the contracted part, the vector part of that. And we know what this formula is. We know that this is what B dot C A minus A dot C B, right? So knowing that formula, we can now blow up this, because this is the contraction part of gamma sub A wedge gamma sub B space-time product with the reciprocal basis vector gamma sub nu. And make sure you understand, this makes total sense. Because this is a vector in the vector space, you can take its space-time product with any other vector in the vector space, which includes this bivector. And so this space-time product's totally legit. But this dot here is telling us, oh, we only want the contraction part of it, which is why we can apply this formula. Right? What we're ignoring right now is we're ignoring the gamma alpha wedge gamma beta wedge gamma nu piece, right? Which would be 0 whenever nu is alpha or beta, because despite the fact that nu is a superscript, it will be in the same, it will be linearly dependent on the subscripted version gamma nu, right? It'll be either off by a sign, or it'll be exactly the same thing depending on whether nu is 0 or 1, 2, or 3. So we're ignoring this for now because we have this formula that's popped up in the text, and we're sort of following our nose with that formula. So now we've got this structure here, which we simplify to this thing here. I guess simplify is a bad word for it, because this is obviously messier than this. That we expand it. And then we have these dot products, which we know by the definition of a vector, and it's we've learned by definition that gamma mu dotted into its inverse, or the inverse gamma nu, is going to be this delta function mu nu. That sort of defines these reciprocal basis vectors, is this expression here, which we learned a few minutes ago. And so because of this, we make the substitution for these two parts in parentheses with these delta functions, delta beta nu, and alpha nu. And then the process repeats itself, but from the left side, and you get another delta function, and then you can expand f. Oh, and the other thing is, throughout this whole process, this 1/2 has to follow us, right? And then in the end, we end up with this expression with 1/2, and then in the end we get f mu nu, right? And it's the antisymmetry of f. By definition, we're dealing with an antisymmetric. We know that this has to be antisymmetric, and the antisymmetry of f is what allows us to combine these two together to get f mu nu. So we have verified this formula. And the other formulas really proceed exactly the same way. In this case, you just do this process twice from the left. And in this case, you're actually doing a bivector product. Oh, that should be interesting. Maybe we should test that one out. And this bivector, this is just notation here. This bivector product is exactly the same as this, because we remember that this rule that gamma mu nu equals gamma nu wedge gamma mu. That rule, that expansion applies for the superscripted or reciprocal basis vectors just as much as it does for the reference basis vectors. And but this might be an interesting one to work out, just to make sure we're on top of our game here. So here I've actually written down this dot product between this bivector, gamma mu wedge gamma nu, and I'm in the reciprocal basis, dotted into the bivector f. Now, the first thing to understand is this dot product, of course, is full of meaning, right? It's the dot product between two bivectors. And that's different than the dot product between a bivector and a vector, which we understand. We know that that is the contraction part of the space-time product of f times gamma nu. The only time we know for sure that this dot product and how to execute it just very naturally is when there's two vectors involved, in which case A dot B is always going to be the Minkowski contraction of A and B. But now we have a dot product between two bivectors, and the paper hasn't really introduced that very obviously, but it has actually introduced it. And it introduced it in this table where you see bivector dot product, f dot g, and it's defined as the symmetric part of the space-time product of the bivector f and the bivector g. And we know that this commutator bracket is defined as fg minus gf over 2. And we've kind of worked through that already. In fact, I think I defined it as f commutator g. Oh, yeah, it's interesting. I just noticed I defined it with an additional factor of 2 than this paper did, right? So I defined the commutator bracket as simply what everybody knows the commutator to be, fg minus gf. They actually throw in this additional factor of 2 in the definition of the commutator. And so, so that's a little different than the definition of my previous lesson. Not that it's really that relevant, because with my definition and theirs, it's all the same. And the point is, it is the grade 2 part of the space-time product of f and g. And clearly, this is the grade 4 part, which means f dot g is supposed to be the grade 0 part, right? So in my demonstration of how to take the space-time product of two bivectors, I would have called this f double dot g, right? And then this would have been f dot g, and then this would have been f wedge g. So, well, actually, this last one, I'm sorry, no, take away that last one. Ooh, wrong. This would have been, well, they don't even have it here. The bivector inflation, bivector inflation. So the point being, though, is that I just want you to take away that they're clearly using the dot product to mean the scalar part, which of course makes perfect sense because what we're after in this formula is a scalar, right? So we definitely want what I would have called the double dot product, but in this paper, they just call it the single dot product. And I have no compunction about not being absolutely locked solid on my notation from the beginning of this lesson and on. Obviously, I don't plan these things out that intensely, and messing around with the notation is how you have to live when you read different papers. And if you really want to study geometric algebra, this one paper isn't going to cut it. And when you go, you're going to have to be real flexible with notation. So anyway, we understand that we're looking for the scalar part of the space-time product of this bivector blade with this bivector f. So first thing I'm going to do is I'm going to take f and I'm going to expand it in the same basis as these reciprocal gamma matrices. So I'll use the reference basis, as the paper calls it, with f. And these are the scalars I'm after. I pull the scalars out, and now I have a bivector product between these two blades in the reciprocal basis and blades in the reference basis. But I demonstrated how to do this before. I'm going to take the Minkowski product of the two that are touching, and then the Minkowski product of the two that are on the outside here. And then I'm going to flip one of them and repeat that process, picking up a minus sign for the flip. And so I get these Minkowski products. And we know that these Minkowski products are these delta functions by the definition of the reciprocal basis. So these delta functions start to appear, and I end up with f nu mu minus f mu nu, which is 2 times f nu mu. Notice it's f nu mu, and I was kind of expecting f mu nu, and in fact, if you go up here, that is what they're calculating. But what I noticed is they calculated it with the reverse, in the reverse, with these Greek indices reversed. And I didn't notice that when I did my work. So notice that this dot product, to get these components, you have to actually take this double dot product, or this contraction relationship, in the reverse order. So of course I end up with f nu mu because I used gamma mu wedge gamma nu. If I had switched it to gamma nu wedge gamma mu, this would have come out to be 2f mu nu. And of course, once again, I forgot my 1/2, right? So the 1/2 has to float through this whole thing, right? And that ends up down here. So this should equal f mu nu. So the trick to getting this right, though, of course, is to understand how to do this bivector contraction, the bivector contraction. And that goes back to the earlier lesson. Okay, so we're pretty comfortable, I think, with this notion of extracting the components, right? The goal is to extract the components from the bivector itself using these different formulas. And notice there are all these different formulas to work with. And this formula here, by the way, is just a restatement of this, right? Because this actually means that, right? And what's also interesting is that this inverse notion applies to these bivectors just as they do to the regular vectors. So the fully covariant version of these basis vectors is also the inverse of the basis vectors. So that's kind of interesting. Okay, so let's go back to the paper. So the paper goes on to discuss in detail how to make this connection between tensors and the architecture of geometric algebra. By the way, I spoke this incorrectly. I said the way this should read is the inverse of the reference basis for bivectors is equal to the contravariant second rank form of the base of the reciprocal basis, right? So the reciprocal version of the basis vectors is still equal to just these up-down indices, even if there's two of them. That's what I'm trying to get at, right? I'm trying to say this, right? I'm trying to speak this somehow, and of course this ends up being gamma mu nu equals gamma mu nu. Wait, gamma mu nu inverse, right? That's what I'm trying to get at. Okay, so next time we'll actually begin the this connection on with tensors as we learned it previously with the formalism of the geometric algebra. So I'll see you next time.